Hi, it's time for another math easy solution here to discuss. So basic continuity part 4 of this series, and look at basically when we look at complicated functions. In earlier videos I went over basic functions and basic definitions of what continuity is, but now let's look at if we have, let's say this theorem is if we have f and g and we're given that they're both continuous at a at x equals a, and c is just a constant, then the following functions are also continuous at a. If you have just f plus g or f minus g, or a constant times f, or f times g, or basically f divided by g if g of a is not equal to 0 because that's not defined. Yeah, so what this is saying, if these two are basically continuous, and if you can add them, you can multiply them, etc., the new function will still be continuous. Now, if we just recap on what it means to be continuous, basic continuity, you have something like this. Limit as x approaches a of f of x, if it just equals to, well, f of a. If you could just plug it in, and then that's continuous. And now proving that these are continuous, well, you could just look at all the limit laws here. We could simply look at, let's just say for the first one, if we just write this one as limit as x approaches a of, well, f of f plus g of x, and then this one would just equal to, now, yeah, limit as x approaches a of, well, f of x. This writing this function like that just means this, f of x plus g of x right here. And now we could just basically apply law 1 for my limit laws video, so make sure you watch that. And law 1 is basically the sum law, so you could break apart this into basically two limits right now. So it's going to be equal to, now, limit as x approaches a of f of x plus limit as x approaches g of x. Yeah, or limit as x approaches a of g of x. That's what I meant. So you have basically this by law 1. And now, since we're given that f and g are continuous, then these equal based on what continuity is, which is, well, just over here, f of x equals f of a right here. So then these just equal to, well, f of a plus g of a right here. And now also, this is just basically plugging in the a value, and this one also, you could write it in that other way of writing a function, and write f plus g of a. And basically now this is, when we look at this above right here, limit as f plus g of x goes to a, if it equals to just plugging in a, then basically this is proof that it's continuous. So this is proof. I'm not going to go over the other proofs for the other ones because it's going to be straightforward. It's basically apply the limit laws and you're going to find out that it's the same thing. Okay, now the last part of this video I just want to cover is quickly the direct substitution property. If you just recall from it, in my earlier video I showed and I proved that this is the case. I also went over it. Basically, direct substitution is if f is a polynomial or a rational function. Just make sure you watch the video links below on what these are and also the proof for this. And a is in the domain of f, then basically you have limit as x approaches a of f of x equals f of a. So if you could just plug it in or directly substitute the a into this x, then this also follows the terms for continuity. So then this, or these polynomial and rational functions, are continuous. Basically, thus we have another theorem. Basically, what I just stated just before this is basically all polynomials are continuous everywhere, meaning negative infinity to infinity, and all rational functions are continuous everywhere where they are defined. And rational functions are just basically, if you have Rx, is just equal to a polynomial. If this is a polynomial divided by, let's say, q, and polynomial. So it's basically a polynomial divided by a polynomial, and they're defined everywhere except this place where q of x is not equal to 0. So that's the only place not defined, and I'm not going to go over too much on this, but because basically I went over the direct substitution, I proved it for both of these cases. And yeah, so basically since I proved that this is the case, then they have to be continuous. Well, that's all for today. I just wanted to go over this briefly. I'll do a couple examples in next video, and that's all for today. You can download these notes in the Dropbox link below, and stay tuned for another math easy solution.